We're going to talk now about psychoperceptual coding and MP3. The whole basis of psychoperceptual coding is that we cannot hear every little detail that's actually present in a sound. And one of the main reasons for this is a phenomenon known as masking. So this diagram is about masking in the frequency domain. Here we have a frequency axis and amplitude. So this might remind you of the Fletcher-Munson curve. Here's the quiet threshold. In other words, the threshold below which we hear nothing. And suppose that instead of doing the standard Fletcher-Munson experiment, we output a very loud sinusoid called the masker, and here it's over 100 dB. And what this diagram says is that, of course, we still hear nothing below this threshold of hearing, but now the threshold of hearing frequencies close to that of the masker become much higher. So what the picture shows us is that everything below these dashed lines becomes inaudible. So we can have a quite loud tone, such as this one, up at 60 dB, and quite a bit higher in frequency, and yet it's inaudible because of this masking effect. And of course, this is important for coding and compression, because if these sounds are inaudible and we leave them out of some encoding of the signal, then the listener will not be able to hear the difference. A similar thing happens with time. So this is called temporal masking. Suppose we have a very loud sound, and then we suddenly stop the sound and we play some other sound that's quite soft. If the soft sound is soft enough or close enough in time to the loud masker, then it also becomes inaudible. So this is time in milliseconds showing the masking curve, the temporal masking curve. And what this says is that, well, let's say 100 milliseconds after the masker, this sound could be down, let's say 40 decibels, and it would be inaudible. And a very interesting thing is, look at the curve over on the left of the masker. So this is saying that even a few milliseconds before the masker, we have masking effects. So a sound that would be completely audible all by itself can be masked or can be made inaudible even after it happens, if the masker comes within a few milliseconds. Let's take a look at some masking in Nyquist. We'll actually do some masking. I set up these functions so that we have a mask, which is, where is it? Noise. Here's noise. It's a noise, white noise pulse with a duration of 0.1 seconds, and it will be at full amplitude. We also have a tone here that's generating a sinusoid with a duration of 0.1 second. And all this other code is making the noise pulses repeat twice per second at the beginning of every period. So the noise will last for 0.1 second, and then the sinusoidal tone will come after that for 0.1 second. So we're talking about temporal masking of this tone. And let's, first of all, I'm going to set the gain to 0.01, where I believe no masking will occur. And let's take a listen to that. The noise will be fairly loud here, so just a warning in case you've got headphones on. You might want to turn down the volume and repeat this a couple of times to get the volume right so you can hear it without any pain. And so here we go with noise and tone together, followed by a couple of pulses of the tone. Okay, so to my ear, the sinusoidal tone is clearly audible in both cases, but if we reduce it by a factor of 10, My claim is that it will be inaudible or close to inaudible with the masking, but when the masking is removed, it's clearly audible. Of course, soft, but still very audible. So your results may vary depending on whether you're listening on headphones or speakers and how loud it is. But if you would like to do some more experimenting, you're welcome to take the code and play with the parameters. The ear operates as a filter bank, at least in a crude model. The loud sound in one channel of this filter bank masks soft sounds in adjacent channels. And so when you want to encode sounds efficiently, you can quantize the sound in these different channels as much as possible using masking to hide the quantization effects. So effectively, we use fewer bits because the differences are masked by masking. The other idea is that we can represent the sound in these different filter banks using lower sample rates because the filter bank, each channel of the filter bank has a lower bandwidth than the full signal. Here's a little bit of insight into the frequency domain and how we do coding. First of all, PCM is time domain. Each sample follows the other in time. And there's not too much sample-to-sample correlation. I mean, we saw that in delta PCM, for example, doesn't really bias a whole lot. That's because the sound is changing all the time. However, spectral data tends to be more static. The spectrum at time t is a pretty good predictor for the spectrum at time t+1. And furthermore, in tonal music, the spectrum is relatively sparse. It's non-zero only where there are sinusoids. And this makes the signal easier to encode efficiently. For all of these reasons, we do perceptual coding using frequency domain representations. Another point is that you might think that if we separate the signal into different frequency bands and encode those bands separately, which is what we do in MP3, you would expect each band to take the sample rate times time in order to encode it. And so you think if there are n bands, now you've got n times the original sample rate to deal with, which would be kind of an explosion of data instead of data compression. However, if we think of this band in the frequency domain, here's the band we want to encode. We could, for example, multiply this by a sine wave at the center frequency, and that would shift the band downwards and upwards. We could recover just the downward shifted band, and now the band has a very narrow bandwidth, and we know from sampling theory that we can sample this at a lower sample rate. In fact, we get to sample it at 1 over n if there are n bands. And so therefore, we recover everything we lost in going from one band to many bands. And data compression, of course, takes advantage of this. When you want to recover the signal, you've encoded all of these bands at very low sample rates as if they were centered at 0. So once again, we just multiply it by a sine and frequency shift the band up to where it was originally. Let's talk a little bit about MP3. First of all, MP3 is shorthand for MPEG Audio Layer 3, and it's part of a broader video compression standard. The MPEG standard for video was designed to allow compatibility between different devices and to eliminate, just a proliferation of different coding techniques and lower cost, increased convenience, and so on. There are also some legal and intellectual property issues dealing with all these encoding techniques, and part of MP3 and MPEG has to do with licensing and making sure that you can furnish an MP3 encoder or decoder and not get into trouble or patent cases or copyright infringement cases. MP3 is a standard for consistent decoding. So the encoding details are not specified. There are some reference encoders, but you can build encoders to go faster or slower, higher quality, lower quality. The only thing MP3 says is when you give me a certain number, a certain set of bits, here's how those bits will be interpreted and decoding. So you can choose those bits any way you like. A 6-to-1 encoding of 48 kilohertz audio is said to give no perceptual difference. This has been verified through extensive testing. Fraunhofer, who is one of the principals involved with the MP3 standard, claims 12-to-1 encoding. Let's look at what happens in MP3. First of all, we use a filter bank. The signal is filtered into 32 bands of equal width, and each band is subsampled by a factor of 32, as we described earlier. There are some simplifications. These bands have some overlap. The bands are actually wider than 1/32 of the sample rate, so the subsampling causes some aliasing. And the filter and the inverse defined for MP3 are slightly lossy. So there is some loss there, but it was deemed to be not too bad. Step 2 is we use a psychoacoustic model. We don't really know exactly how masking is going to behave, but we can build models, and part of the difference in different encoders is slightly different psychoacoustic models. The question is, how much can each band actually be quantized, or how much error can we introduce into the coding? We take a 1024 point FFT of the audio, and we group the spectrum bins into critical bands. This has to do with auditory perception. We identify the tonal components, in other words, sinusoids that appear as peaks in the FFT, and assign a tonal index to each critical band. And that's because in the psychoacoustic models, masking due to sinusoids is different from masking due to noise. So we have to, roughly classify each critical band as either a sinusoidal energy or noise energy. And then from the spectrum, we compute the masking threshold for each of the 32 subbands, and then compute the signal to mask ratio for each of the 32 subbands. In other words, if the masking threshold is, let's say, 40 dB and the signal in that band is 50 dB, then the signal to mask ratio is 10 dB. To do coding in MP3, each subband is transformed with a modified discrete cosine transform, or MDCT, of length 18 or 6 subband samples. The discrete cosine transform is similar to a FFT, but it has nicer properties in terms of boundaries, doing overlap adds, windowing, and so forth. The discrete cosine transform is very popular for data compression, both of audio and images. DCT is used in JPEG coding, for example. If there's only one sinusoid in the subband, then only one discrete cosine transform coefficient should be high, the others will be low. Finally, we quantize these MDCT coefficients according to the signal to masking ratio. There are 576 coefficients per frame. That's 18 coefficients times 32 subbands. We order them by increasing frequency. Remember, we're in a sort of a frequency domain here. And so these coefficients represent amplitude or weights on different frequencies. The highest frequencies tend to be zeros, just because the combination of masking, threshold of hearing, and just the way audio signals tend to have less energy at high frequencies, a lot of the high frequency coefficient will be zeros. Part of the encoding of the output is that all the zeros at the top end of this list of coefficients need not be encoded at all. As we come down in frequency from this run of zeros, the next thing you find is a run of mostly -1, 0, and 1. And so these bits are encoded 4 at a time into an alphabet of 81 symbols. We'll talk about that a little bit later. And the remaining values are coded in pairs. So this may seem very ad hoc and very strange. In some sense, it is. I'm sure the designers of MP3 and other coding standards considered lots of different ways of doing encoding, and this one just happens to work out quite well. The way the coding is done relies on Huffman coding. So you may be familiar with Huffman coding already, and if you know it very well, feel free to skip ahead. But I want to describe Huffman coding because I think it's a very important technique in information and computer science, and it's directly used in MP3 coding, so it's good to know about. Huffman coding is probably the most popular technique for removing coding redundancy. So here, we're concerned that we have these coefficients which are treated as individual symbols, and we want to use as few bits as possible for those coefficients. Huffman coding gives the smallest number of code symbols per source symbol. So in other words, code symbols are bits, and we're encoding the source symbols, which are these coefficients, into bit strings. The symbols are coded one at a time, so there's no inter-sample redundancy being used in Huffman coding, which is sort of a weakness or limitation. The codes are variable length, and so we choose the codes, a binary code for each symbol, to minimize the expected bit length. Here's an example. Suppose instead of encoding numbers, we're going to encode letters of the alphabet. In fact, we're only going to encode A through F in some strange message that only uses the first few letters of the alphabet. And we know from experience that the expected frequency of A is 0.2, and B is 0.1, C is 0.1, and so on. So there's an uneven distribution of these symbols, and it follows that, let's see, the most popular one, E, at 0.5, should use less bits than the unpopular symbols like F, which is 0.0, only occurs 0.07 of the time, or D, which is only 0.03. So the way we proceed with Huffman coding is we start with the least frequent symbols, D and F, and we enter those into a tree where one branch is designated by 0 and the other branch is designated by 1. Okay, now we take the sum of frequencies of D and F, which is 0.1, and now we are going to consider 0.1 to be a symbol. And we look again for what are the two least frequent symbols. And, well, we have two choices, B and C, but here we'll take C, and we construct a new symbol, which is the combination of C and this 0.1 over here, and this occurs with frequency 0.2. And we continue along, we add B, and this adds up to 0.3. What's left? We have A at 0.2, we have this 0.3, and we have 0.5. So 0.2 and 0.3 are going to be combined. We have a frequency of 0.5, and now we combine that with E, and we complete the tree. Now, if we proceed down the branches of this tree, we get strings. So 0, 0, that is going to be the encoding of A. the single bit 1 will be the encoding of E, and the longest code that we have is for D and F. F, for example, is 0, 1, 1, 1, 1, because that's the path to F. So here are all the possible paths and the encodings. So this is, again, a variable length coding. The shortest code is for E, the longest code is for D and F. And if we want to encode a message like ABC, we simply take the bits for A, concatenate the bits for B, and concatenate the bits for C. And it turns out you don't need any kind of framing or indication of how long these codes are, because just by following this tree, whenever you reach a leaf on the tree, you know you're at the end of one symbol and you can start the next symbol. In this example, the average length is the length of each code multiplied by the frequency with which we would see that code. So here we have A is of length 2. It occurs with a probability of 0.2. Encoding for B has 3 bits. It occurs 0.1 out of 1 times a probability of 0.1. And we continue adding these up, and we get the result is that this code requires 2.1 bits per symbol on average. That's the expected length of the message. So 2.1 bits, we could, if we had a non-compressed representation, what would we do? Well, we have 1, 2, 3, 4, 5, 6 symbols, round that up to a power of 2, and get 8. We can encode 8 things with 3 bits. So in some sense, we've gone from 3 bits down to 2.1 using Huffman codes. Now, with MP3, the coding is used to encode some very small numbers. Remember that one thing we use Huffman coding for is to code this run of efficients that are either -1, 0, or +1. That's only 3 values, and so using a Huffman code for those 3 values is not going to save too many bits. Each of those values. Well, we could certainly encode each one of those with 2 bits. 1 bit would only allow us to encode 2 symbols. So the way out of this is to group these things, essentially to make larger numbers with a more interesting probability distribution. So we cluster these coefficients into groups of 4. And now, instead of encoding individual symbols, we encode vectors of symbols, of 4 symbols. For example, let's just say that A represents -1, -1, -1, -1. B represents this vector. C represents this vector. So how many? So now we're constructing a new alphabet: A, B, C, D, E, F. There are, as you might remember, 80-something different combinations of these numbers, and so we have 80 symbols to encode with Huffman codes. So that's what we do. Another concept used in MP3 is that of the bit reservoir. So the idea is this: some frames are going to be very efficient to encode. Other frames are going to introduce a lot of information and not be coded so well. So if a frame can be coded with very few bits, maybe it's just silence in the audio, so there's nothing to encode, not too many bits, then that allows us to sort of get ahead of the coding rate. So maybe the coding rate is 64 kilobits per second. If we don't need 64 kilobits per second, we can take the bits that we don't use and in some sense put them in the bank or put them in the bit reservoir. And then later, when we encounter a frame that requires more than 64 kilobits per second to encode, we can withdraw what we put in the bank. We can use bits from the bit reservoir, temporarily exceeding the maximum data rate, but allowing us to do a better job of encoding audio. So in In other words, we're not encoding at a fixed uniform encoding rate, but at a variable rate that statistically overall remains below our limit of 64 kilobits per second, or whatever it is. Another problem with MP3 is, how do we know how many bits to spend on each band? Remember that we're coding these 32 bands differently. And so the bits are allocated to bands wherever the quantization noise exceeds the masking threshold. And this bit allocation is followed by a recalculation of the noise. And this iterative search for how to allocate bits to different bands can make encoding slow. It can make some encoders run better than other encoders depending on how much time and how complex the bit allocation algorithms are. So in summary, masking reduces our ability to hear everything, including quantization noise. MP3 descriptions are highly quantized, but these are frequency domain descriptions that we're quantizing. We're not actually talking about quantizing samples. After we do this quantization of these coefficients, we use run length encoding and Huffman coding to encode the descriptions efficiently.